Thank you. I would like to start by thanking the organizers for inviting me to this very nice meeting. It's a pleasure to give this talk here. The topic, I think, is very much fitting. It concerns a spectral problem. It's definitely in quantum theory, and I think, and there's also differential operators involved. So I think it's quite fitting. So I will start by trying to explain the problem. So this is what is called the polaron model, or the standard example, a well-known example is the Fröhlich model, but let me explain things in a bit more generality. So I want to study the spectrum of the following operator, which is called H here. I'm using sort of standard Fock space notation, sort of standard in say quantum statistical mechanics, but maybe not everybody is familiar with this notation. So let me actually write down the proper definitions. So the operator is defined on Fock space, which is simply the direct sum over n particle spaces, so it's over all n, and then you have the L2, the n particle space, which is simply L2 of Rd to the power n, and the sum stands for permutation symmetric functions. So you have functions of n variables in Rd, and the functions are permutation symmetric, right? And you take the direct sum over all of them, so you have like a space of an arbitrary number of particles. The operator n is just the number operator, so if you maybe allow me to call this thing here Hn, then n restricted to Hn is nothing but n. Actually, it counts the number of particles. P is called the momentum of the field. This is really a quantum field theory. So P is, when you restrict it to the n particle space, it's just the sum of the Ki, I equals 1 to n. That's my notation. So K is the momentum. So if you want to think rather in X space, this is minus I times the gradient. So here's your differential operator. But I'm thinking always in momentum space. So it's just multiplication of a function of n variables K1 to Kn by the sum of the Ki, right? So this is the total momentum, right? So if you want, this is the gradient with respect to the center of mass variable on a function of n variables, and then you just simply take the direct sum over all n. So that's the p here. So you have a p squared, you have an n, and then you have here, this is sort of the interaction term phi, which is a linear term in the a's and a daggers. So I'm using the standard notation of creation and annihilation operators on Fock space, which are sort of often conveniently expressed as integrals over operator value distributions, AK. So you can think of AK as the operator that annihilates a particle, a phonon at momentum K, and integrated against V. I will denote this by A of V, and A plus its adjoint, that's phi. So for completeness, I give you the definition, right? So A of V maps Hn to Hn minus 1. It annihilates a particle, and what it does is simply you take the partial inner product of one of the variables in V, right? So A of V applied to a psi in n variables is a function of n minus 1 variables, and you get it by integrating psi n of K1 Kn against V of Kn, maybe complex conjugate over Kn, right? And then there's, I think there should be a square root of n to make this correct. That's the definition. And A dagger is simply its adjoint, which you can convince yourself acts, well, of course, from Hn minus 1 to Hn. And if you apply it to a psi of n minus 1 variables, right, you get the function of K1 up to Kn, which is simply V of K1 psi of K2 up to Kn, and then you have to symmetrize. So you should really put this a Ki, and here the ith term is missing, and then you sum over I from 1 to n, and then you multiply by square root of n, and then this is the adjoint. Okay, so I assume most of you are familiar with this, but for completeness, we give you the definition here. Sorry? So V, well, okay, I'll come to that. Actually, one should think of V in L2, but actually V doesn't really have to be in L2. Then this is somewhat a formal expression, but this operator as a quadratic form turns out to be well defined under the assumption that 1 plus 1 over K, V of K is in L2. Because you don't really need that V is in L2 only relative to the Laplacian that's sort of there. So it's really with sort of the appropriate measure determined by the inverse Laplacian, it should be in L2. That's really the only thing you need to assume. If V is not in L2, then the domain of definition of this operator is sort of a bit subtle, but actually I don't care because I'm always thinking of this as a quadratic form, and there it's well defined as long as V divided by K is in L2. Okay. So these models arise as the usual. So when I say usual polaron models, what is the polaron? Physically, it models an electron, or in general, say a charged particles that moves through a polarizable medium. So if a particle in the medium, the particle polarizes the medium, that creates a local dipole field, a polarization field that interacts back on the electron. That's the picture of the Fröhlich polaron model. It's a completely translation invariant model, so you can fix the total momentum. Right, so you can look at it at a sector of fixed total momentum, and here I set the total momentum equals 0. That's why here the field momentum squared appears, because in the usual polaron model you would have there the electron momentum squared, but if the electron momentum plus the field momentum is 0, it's a conserved quantity, then you have the field momentum appearing here. Right, so there's no more electron that's sort of out of the picture, because in this fiber decomposition, when you fix the total momentum, you're only left with an operator on Fock space, and that's this operator. That's what I mentioned here. The arises as the restriction of the usual models to a fixed 0 total momentum. Okay, and the standard example I want to keep in mind is called the Fröhlich polaron model, which first of all corresponds to dimension equals 3. For me, D is general, but think of D being 3, and V simply be proportional to 1 over K. Right, which is in particular not in L2, so I don't want to assume L2, but it does satisfy the property that V times 1 plus 1 over K is in L2. Okay, and then this is a well-defined semi-bounded operator, and so it defines a semi-bounded quadratic form, and therefore a unique self-adjoint operator, and we're interested in the spectrum of this operator. Okay, and maybe I can already go one step ahead and see what to expect, right? So you can first look at the trivial case when there is no interaction. So when this V is 0, right? V is sort of my only parameter in the problem, right? That's this function V. Maybe it has at least a coupling parameter like here. So if V is 0, then, so what is the spectrum? Well, then the operator itself is, of course, just the direct sum of operators. There is the vacuum corresponding to n equals 0, right? In which case n is 0 and also the momentum is 0. So that's just the 0 eigenvalue, right? So the spectrum of H will look something like this. There will be the 0 eigenvalue here that corresponds to n equals 0. Now the next sector is n equals 1, right? So then, of course, the number operator is 1. And here you just have the Laplacian, right? So that's the one particle sector. That's the Laplacian plus 1. So, of course, the spectrum starts at 1. So this distance here is 1. And then you have a completely continuous spectrum here. Right? So if there is no interaction, the spectrum consists of a single eigenvalue at 0 and then continuous spectrum starting at 1. And of course, you have all the higher particle number sectors. They start at 2, 3, and so on, but they also just give you a semi-axis of continuous spectrum. Now, if you turn on the interaction, if you turn on the V, it turns out that picture stays the same in the sense that the whole spectrum simply moves to the left. But this gap here is always 1. So there is always the ground state energy now, which will be a negative number. It moves to the left. But in some sense, it drags the whole continuous spectrum along. The gap to the essential spectrum is always 1, because the 1 is sort of the energy that it takes to create one additional phonon which you can move freely, so to say. That's the picture. So you have sort of here the bound system that has a ground state, and then if you're willing to spend an energy at least 1, you can create an additional phonon which doesn't interact with anything else, sort of moves behind the moon, and can have continuous spectrum. Okay, so that's the picture. So here I think it's described in more detail, right? So E0 I will call the ground state energy. That's this number here. And then it's well known that the essential spectrum is simply the half line from E0 plus 1 to infinity, right? That's here. What I'm interested in is whether when you turn on the interaction, something happens in this window. So in particular, the question is, can there be additional eigenvalues? Right? We know where the essential spectrum is. We know there's a ground state. The question is basically what happens in here. Are there additional eigenvalues? This will be my spectral problem. And the reason, the way we got to this is that actually in some sense, well, maybe in some sense you could say by accident, by studying this, the Fröhlich model at very large coupling, we discovered recently, this is joint work with postdoc David Midruskas. In fact, it says in the preparation here, but it appeared on the archive today, so I think it's actually complete. So we can prove that there's actually lots of eigenvalues for the Fröhlich model. If you send the coupling constant to infinity, you go to very large interactions, you get more and more eigenvalues appearing in the window here between the ground state energy and the essential spectrum. And in fact, their number increases beyond bounds. So if you send the coupling constant to infinity, the number of eigenvalues actually goes to infinity. So I will not talk about that. This is more of a motivation to ask the question, well, what actually happens for small coupling? Right, so this is for large coupling. It's a very actually delicate asymptotic analysis. It's complicated. I mean, I think it's a 50-page paper, which I do not want to talk about. But the question actually arises, is that really an effect of large coupling, or is it actually always there? And my first thought was, well, that must be known, right? Small coupling is sort of perturbation theory. We know that the ground state energy as an analytic function here, everything I thought can in principle be computed by perturbation theory, so I thought it must be known what happens for small g, and I was surprised to find out that it's not. And I think there's a good reason why it wasn't known, because it's actually very subtle. That's what I would like to explain here. That's the purpose of this talk. Okay, so we can talk about Fröhlich, but we don't have to. It applies to this much more general setting. Basically, I take an arbitrary interaction, right? I scale it by a coupling parameter such just so that I can talk about small coupling, right? So if you want fix a W, multiply it by a G, that's a small number, and we study the spectrum for small g. Okay, and in particular, we want to know, are there additional eigenvalues in there? Now, we can, I guess in some sense, simplify the problem to really reduce it to a one-particle problem via the well-known Schur complement formula. Right? So basically, right, our Hilbert space decomposes into this direct sum, but we can just look at the one-particle sector, and the Schur complement formula tells us that if we have an eigenvalue of H in this window between the ground state energy and the essential spectrum, then there is a negative eigenvalue of a corresponding one-particle operator, which I denote by O here, and it's just the following, right? So you just, first of all, you project your operator to the one-particle sector where it's just k-squared, it's just the Laplacian, okay? I subtract the energy I'm interested in, which is really the energy here, which is E0 plus 1, but the 1 was there because the operator had a particle number 1, right? So I have k squared plus 1, but I subtract E0 plus 1, so that's this thing. And then, of course, you have the coupling to the other sectors. You have the coupling to the vacuum sector, and you have the coupling to the sectors with particle number larger than 2. So that leads to this effective operator. The coupling to the vacuum just leads to this rank 1 perturbation, which is positive. It's just I use this standard physics bracket notation. This is the rank 1 projection onto the vector V. I use it even if V is not in L2, keeping in mind that at least relative to k squared, this is a bounded operator. Okay, and then the D is more complicated because that's the guy that sort of creates the coupling to the sectors with particle number at least 2. And explicitly, if you just use the Schur complement formula says what, right? You have to take the operator, you project it onto this sector. So that's the pi is simply the projection onto the part of Fock space where the particle number is at least 2. So in this direct sum, the projection onto n bigger or equal to 2. Right? So I project the operator to this sector, I take its inverse, right? That's what I call X as an operator, of course, on this subspace. Then here is the operator that maps between the two subspaces, right? So that's the A here and the A dagger that maps me down to the one particle space, and pi1 just means the projection onto the one particle space, right? Because this D is an operator just on the one particle space. So pi 1 projects onto the one particle space. Okay, so this is nothing but the Schur complement formula. So we want to know whether this operator, which is now a one particle operator, if you want, it's like a Schrödinger operator, right? It's a Laplacian plus something. Well, the something is a bit more complicated than a potential, but in any case, we want to know whether this guy has a negative eigenvalue. That's our, that's what we're tasked with. Now, in order to look at this closer, we have to look closer at what this operator D actually is, right? It's sort of an abstract thing, but it turns out one can simplify it quite a bit. One can sort of move things around. This is what is usually called pull-through formula. One can basically compute what happens if I pull an A or an A dagger through the X, it shifts things around. And if you do this, it's a little computation that didn't work out in detail, but let me just tell you that the D is a sum of two terms. One is a multiplication operator. So I write it as EK. This just means that it's a multiplication operator in K space, okay, by a function EK, which is nothing but, it's explicitly written here, it's the expectation value in V of an operator that's called YK. And the YK is a bit like the X up there. The only difference is that the -1 is not there. And you project now onto particle number at least 1, right? So here is at least 2, here you have at least 1. The 1 is missing, and the field momentum is shifted by a K. That's why there's a subscript K here, right? K is just a number in RD. Okay, so here's explicitly the Y. Its expectation value gives you a function, and that function defines a multiplication operator, EK. Okay, that's part of it. The rest is actually a much nicer object. It's something that has an integral kernel, right? So this R, and this R has an integral kernel that's actually proportional to this function V. So the R of K and L is VKVL times a certain number, which is written out here. Doesn't look very nice, but that's what you get when you do this pulling through. So there's another operator appearing that is called Z, right? So there's an X, a Y, and a Z now. They all look very similar. X has projection onto at least 2 particles, Y at least 1 particle, and the Z does not have a projection anymore. This guy has a -1 here, this guy has nothing, and this guy has a +1, right? And it's also the shifting here of the field momentum by a K. So this is just my notation. I will use it later again, but of course I don't expect you to remember this formula. I mean, it's just the formula that's there. It's a computation you can do. Yes? No, it's not the same thing. I mean, of course you can say you can prove the existence, you can try to prove the existence of excited eigenvalue by finding a test function, or finding 2, say, because 1 exists in any case, that's the ground state. Finding a orthogonal 1, that you could do, okay? I would not advise it. No, you'll see why. Maybe that's the first thing I tried, but didn't get very far, okay? So the bottom line is the operator we want to study is a multiplication operator, which is basically the Laplacian, multiplication in K space. Of course, it's then changed by a function that's, you see, that's EK minus E0. And by the way, this notation is justified because if K is 0, this is indeed the ground state energy. That's just, again, the Schur complement formula applied to the vacuum sector this time. Okay, so it's an operator that's basically the Laplacian. There's a small perturbation, small, right, because I hide the coupling constant whenever I write V. So whenever you see a V, you should think this is actually something small at weak coupling, right? Then there's this rank 1 positive term, and then there's another term, which is also an integral operator with an integral kernel that's proportional to VKVL, right? I say also because, of course, this operator is also an operator whose integral kernel is simply V equal to VK times VL, right? It's a rank 1 thing. Okay, and one thing that will be important is if you look at the prefactor, right? This guy has a positive prefactor, which is basically 1 at small coupling, right? Because E0 goes to 0 as the coupling goes to 0. If you look at this guy here, there's all this complicated stuff, but I'm saying it's also 1 at weak coupling, right? Because if you send the coupling to 0, this term disappears, all the V stuff disappears, you're just left with the vacuum. I should have said that also. Omega is the vacuum vector. Everything disappears, you just get the Z, but on the vacuum in leading order, that's just 1, right? Because this term vanishes, here everything vanishes except for the 1, okay? So at weak coupling, R is also to leading order simply minus VK, VL, which cancels exactly that guy. So that will be important, that somehow there's a cancellation between this positive rank 1 guy and this more complicated guy, which, however, to leading order is sort of cancels that guy. Okay, this will be important. That's why I emphasize it here. Okay, so here it is once more. Our effective Schrödinger operator, whose spectrum we want to determine, or in particular we want to answer the question whether there is a negative eigenvalue, is of this form. It's basically a Laplacian multiplication operator in K-space plus something that has an integral kernel, and it's of the form, I write it here short like that, that's just short for an operator with integral kernel Vk, Vl times some function g of k and l. Okay. Now, there's already one subtle distinction. So we do the weak coupling, right? So all this stuff is small, right? Now, I want to argue that if it's still small when I divide by k, then clearly this does not have a negative spectrum, right? Because by the Biermann-Schwinger principle, when you just pull out the k, right? Pull out the k to the left and to the right. If you can divide this guy by k from the left and from the right, and it's still small, you get 1 plus this thing, right? So it can never be negative. So this is what I call the infrared regular case. So if v divided by k itself is in L2, and infrared refers to that this is sort of a condition close to k equals 0, right? Then clearly there's no negative spectrum if at small coupling. This is sort of really the perturbative regime. In fact, this is all well understood. I found a paper by Minlosch in the 90s. I think there are others. And in particular, actually, I want to refer to this PhD thesis by Dahlbeck. He was a student of Jakob Schach-Möller in Aarhus, and he wrote a thesis in 2017, which investigates this problem. And actually, I think pretty much everything I learned about this problem, I learned from his thesis. So this is very nice work. In particular, he had this conclusion, right? Now, this is, however, not the case we're interested in. In particular, right, in the Fröhlich case, it's not the case. In 1 or 2 dimensions, this will basically never be the case, right? Because you have a 1 over k, so this is not locally in L2. So we are more interested in the infrared singular case, right? So there I cannot simply argue by pulling out a k to the left and to the right, right? Because then I get a singular object, okay? So now to, however, sort of extract this singularity, we simply do the following, right? We look at this integral kernel here, this g of k and l, and the problem is at k equals 0, right? So let's just expand it, if you want, at k equals 0. So let's write it as a constant, which is simply its value at 0, plus a function which is simply here. I mean, psi of k is just g of k of 0 minus this constant, right? So if I write g as c0 plus psi of k, psi of l plus f of k and l, this is the definition of f. Then, of course, you see that f vanishes if either k is 0 or l is 0. Right? So I simply extracted the constant and the rank 1 stuff, so to say, that sits at the singularity, namely where k and l are 0, and this stuff is therefore then 0 if either k or l are 0. Okay? So I just do this decomposition. That's my definition. I plug it in there, right? So you see, if I now use the usual bracket notation, you see the O is k squared plus ek minus e0. So from the constant term, you get a constant times this projection in the v direction. There's sort of the mixed terms where you have v against psi v and its adjoint, and then there's the regular stuff vfv. Okay. Now I simply complete the square. You see, these guys are sort of singular, okay, but I complete the square and get a lower bound, which is then simply 1 over z0 times the projection in the direction of psi v. Right? This is now also regular, right? Because psi is a function that vanishes at k equals 0 by construction. So this is also a nice object, even after a divide by k. Okay? So I have the lower bound, k squared plus, well, this stuff. There's the regular stuff, and then there's this minus rank 1 projection, right? And what will be crucial, comes back to what I just said before, this constant c0 is small. Right? I told you this constant c0 vanishes in the weak coupling limit because of this cancellation I just pointed out. So c0 is small, but I divide here by C0. So this object here will actually be order 1. It looks like it's order g squared because there's a v squared, but C0 itself is order g squared, so this thing will be order 1. Okay, so this will be important. I'll come back to that. Okay, in any case, I have this lower bound, and now I do sort of the Biermann-Schwinger, the usual thing. I mean, I pull out the k, right, and the remaining thing I just call S. Okay, so here is explicitly S, which I want to call the Biermann-Schwinger operator, right? It's 1 plus some nice function, ek minus e0 over k squared is a bounded function, actually. I mean, because ek is very regular, and it's order g squared, so it's a small thing. And then I have something that's also regular, right? Because f is this kernel that vanishes on either of the with either k or l are 0. So I have this object here. And then I'm still left with this rank 1 term here, which is also regular because psi vanishes at 0, right? But it's order 1. Okay, so think of this operator as 1 plus something small, that's this stuff, that's order g squared, minus a rank 1 projection onto some function that I call phi, okay? That's what is written here. This thing is also order 1. It's not small in the weak coupling limit. This guy is small in the weak coupling limit. Okay, and what I want to know is, does this guy have a negative eigenvalue now? Right? Now it looks very simple because it's a rank 1 problem, right? A clearly does not make things negative, if you want. That's a small thing. Phi is order 1, so the question is basically, is the norm of phi bigger than 1 or smaller than 1? That's the question it boils down to. Okay, so here I've basically just rewritten the same thing what I just said. We have to check for positivity of this sort of Biermann-Schwinger operator, 1 plus a minus this rank 1 projection. A itself is small, it's order coupling squared. Phi is not small because of this cancellation, it's actually order 1. Okay? Now, of course, if you think about it, if g is small, of course, basically positivity of this is equivalent to the positivity of simply this number, right? Again, I pull out the 1 plus a, which is invertible, so you get a 1 minus the expectation value of 1 over 1 plus a in the vector phi. Okay, so now we've reduced the problem to just computation of one number. Is this b negative or not? That's what we need to know. Okay, and now we cannot compute the b, of course. I mean, at least not a priori. So we could try to do some perturbative analysis and just look at what it happens at weak coupling, right? Let's just send coupling to 0. And then the first interesting thing I think happens, and this was already observed in this thesis by Dahlbeck, you cannot conclude anything because in the limit it's actually 0. If you remove the interaction, this b is 0. We want to know whether it's negative or not for small b, for small g, but if a g equals 0, it's 0. We don't know what it does for small g. And you see, this is sort of intriguing already because you see, we started with something that without interaction was equal to 1, right? So think if here is the interaction, and here, if you want, is the eigenvalue, the lowest eigenvalue of the Biermann-Schwinger operator. Without interaction, you start at 1, right? The operator is just a Laplacian. You pull out the k to the left and right, you have 1. So you would think that you start at 1. And this is actually true if you look at the infrared regular case. Then perturbation theory basically means you start at 1. It will do something. Clearly, it will not reach below 0. So you cannot have a negative eigenvalue at small coupling if it's continuous. But now here something discontinuous happens in the infrared singular case. In some sense, as soon as you turn on the interaction, you jump from 1. It's discontinuous, and you happen to jump exactly to 0. So this is already kind of intriguing. I mean, I don't see any a priori reason why this jump has to go from 1 to 0, right? It could go here, or it could go here. I don't know, but it happens to jump to 0, which, however, leads to the dilemma that we don't know whether it's positive or negative for small g. Okay, so this was already observed in this thesis by Dahlbeck, who basically says, well, to conclude, to know whether there are negative eigenvalues or not, we have to go to next order. We have to actually compute the derivative, right? We have to really expand. And for lack of anything better to do this summer, I started to do this. Now, things are clearly ordered g, right? Everything is even in g. You can convince yourself there's some unitary that takes g into minus g, so it's always expansion into even powers. So I computed the next order, and lo and behold, the answer is 0. So I would say wasting 2 days of my life. I also didn't quite know what I was doing. You see, it's also a bit, when you say g squared, you have to keep in mind that you really have to expand to power g to the fourth, because there's this cancellation. You always divide by something that's order g squared. So this is really computing things to fourth order, which is a pain. And I did it, and I was disappointed because after 2 days of calculations, the answer was still 0, so I was left with nothing. Now, maybe more reasonable people would have given up at this point, but it was the end of the summer. I had time, and I really didn't know what else to do, so I kept on going. I spent endless hours, evenings, calculating pages of pages. My wife was getting seriously worried, I have to tell you. And she predicted, she told me after all of this, the answer would be 0. And the reason is that when she studied at university, she told me that if the professor wrote down some lengthy, incomprehensible formulas at the blackboard, the answer at the end was always 0. So she predicted it, and she was right. So it took me 2 weeks to convince myself that actually also the next order is 0. Also, if you calculate up to order g to the 6, it's still 0. Now, then I was sort of, I guess, reasonable enough to, I think I gave up for a week or two, but I couldn't sleep. I mean, I thought there must be something, or there must be a reason. I mean, this cannot be a coincidence. And I started thinking about it. I mean, I kept thinking about it, and eventually I sort of discovered some structure in these tedious expansions, which led me to actually conclude at the end that b is identically 0. So this function here that we're computing as a function of the coupling constant is actually 0. Okay, that's the ultimate theorem now. It's of course 0 only, I mean, we don't know, eventually, something might come in from here. It's 0 for small g. Everything is perturbative, so there will be eventually, in fact, we know eventually there will be negative eigenvalues, but we know for small g there are none. And the reason is that this Biermann-Schwinger eigenvalue is exactly 0. So it's basically the system is always critical, right? So you're used to, I think at least that's how I think of Biermann-Schwinger, right? If you think of just a Schrödinger operator, right? You start with something, you turn on the coupling, eventually you're going to hit 0, you get the negative eigenvalue. Right? That's the usual picture we draw when we teach this stuff. Here you have a situation where the system is exactly critical, that the lowest eigenvalue is always 0. It doesn't change. It doesn't go up. It doesn't go down. It's just exactly 0 independently of the coupling. It's a miracle. I don't know why it's true. I can prove it, but I don't understand it. Okay, so let me then maybe spend a few minutes on telling you how the proof goes and what I guessed, so to say, to be able to show this. And this is basically a formula for this function phi. Right, so what we have to compute, you see, is this thing here. We have to invert an operator that we don't know explicitly, but it turns out there's a nice formula for 1 over 1 plus a applied to phi. This is what I sort of guessed just by expanding. And once you know what to look for, you can check that it's true, and it turns out to be true. So here is the formula. Okay, sorry, and I should conclude. I mean, if you paid attention, you know what the theorem is, of course. The consequence of all of this is that there is no excited eigenvalues at weak coupling, right? So here I wrote it as a theorem. So there exists some G0 that for small coupling, there is no excited eigenvalue, so the spectrum is exactly just the ground state energy plus the essential spectrum that starts at 1 plus the ground state energy. Okay, so this is true basically for all these models I mentioned under these regularity assumptions on the interaction. And so the proof boils down to showing that this number b is simply 0. And here is sort of the formula that I mentioned. There's sort of an explicit formula for this function phi that appears at this rank from projection, which involves in particular the operator 1 plus a, which is nice because that's the one I have to divide with, right? So there is this formula. I can just maybe briefly, the notation in principle was explained. So there's this vector v, there's this operator y0 introduced. This is the absolute value of the field momentum, and then you project it down to the one particle sector again, right? Because this is an operator on the one particle sector. This is a one particle vector. Okay, so this is one thing. right? We have to compute phi 1 over 1 plus a phi. So if I divide by 1 over 1 plus a, this guy is gone. So I still need the inner product of this vector with phi, which is written here. And this, it turns out, has an explicit formula, which is given in terms of this constant C0 introduced. And if you just plug in the definition of B, you see from these two identities, you simply get that B is 0. Now, where do these identities come from? And that's, then I have to sort of go back to this complicated objects, right? So where the phi was defined. Maybe I still have a few minutes. I just remind you of where the phi came from, right? So here was the definition of the vector phi. It's basically up to a constant. It's psi times v divided by k. Okay, now what was psi? Psi is defined here. It's g of k of 0 minus g of 0 and 0. Okay, and then what was g? Well, I have to go back once more. That's the g. I mean, the g is, sorry, this constant here minus all this stuff. Okay, so it's as complicated as that. That's what it is. I think there's a priori no nicer way. Well, initially, I think there's no nicer way to write it, but it turns out there is, namely, I can write this phi. So as a function of k, I can write it this way as lambda 0 minus lambda k, where this, this is just a definition. Sorry, I just this is basically using the formulas I just flashed again, plugging in the definition. That's what this was, right? It involves these operators, the x's, the y's, and the z's. But it turns out that there's quite some simplification, and you can write it like this. Okay, that's the calculation I'll come back to in a second. This involves this operator d, right, which is explicitly in our A, in the one particle operator we're interested in. And this is just, this just means that as a function of k, right, this is this vector v times lambda is equal to that vector, right, projected down to the one particle sector. Okay, and once we know that, together with a resolvent identity in this form, you get the following identity, that this function v times lambda, which is what we want to compute, we can express like this as a sum of these two terms that involve, in particular, this operator d. And now if you compare with the definition of A, you get this identity for our vector phi. I realize, I don't expect you to follow this in any detail. It's just that, I needed to sketch the formulas to sort of explain what's going on. The point is that I get an identity for my unknown function phi, which involves a vk over k times some constant. In fact, the constant is expressed in terms of explicit constants and something that I would like to compute actually, because it involves the phi again. Right? This comes from these rank 1 terms in the definition. And then there's some other vector. In fact, that was the claim that is equal to the phi, basically. So this is the identity I get. And now comes the crucial point that this vector here is not in L2, right? This was our assumption. We were in the infrared singular case where this vector is not in L2. I know that phi is in L2, and this vector is also in L2. This you can easily convince yourself. But since this vector is not in L2, I know that this unknown constant here in front must vanish, right? So that tells me what this inner product is, right? I didn't know what phi is, but I can tell you what this inner product is because I know that this term in square brackets has to vanish for this vector to be in L2. But once this thing vanishes, of course, then I have a formula for phi, okay? And that was the claim. Okay, so this identity gives me two things. It gives me a formula for phi that involves the 1 plus a, right? And it tells me what the inner product of phi with this remaining vector here is. So it's all very miraculous, but it all works out and it gives these identities. So okay, I have one more slide that this is just a calculation. The key thing, if you want, is this what I called the lemma before. It's an identity for this sort of complicating looking object which defined my function phi, or part of it, in terms of something that looked much simpler. It involves the objects that we wanted to have actually. Okay, and this is an identity you can check using 4 different identities that you have to use in various forms. Here's explicitly these pull-through formulas that I already mentioned that tell you what happens if you pull through say in this case, an annihilation operator through these resolvents, right? These x, y's, and z's, they were basically all various forms of resolvents of our operator with some projections in there on different particle number sectors. So you can just convince yourself of this identity by basically first applying it, dividing by x on the left and on the right, and then it's just an explicit computation. And similarly here, you have these two pull-through formulas that basically tells you that if you pull an a through an x, it becomes a y, and if you pull an a through a y, it becomes a z, okay? And there are correction terms, okay? So these two things you need, and then there are two other things which are a bit like resolvent identities, right? Because these y's and the z's, the x's, they're all resolvents, right? So it's like the difference of two resolvents is like a product of resolvents. Right? This is not exactly true because there are all these projections in there which doesn't quite make this a resolvent, but if you work out their effect, you see that there are explicit correction terms for these resolvent identities. So I claim that with these four identities, you can basically convince yourself that this thing is true. I don't know how you would have ever guessed it if you didn't know what you were looking for, basically. But since I suspected this to be true, I managed to actually show it using these identities. So I think that basically brings me to the end of my talk. So here is just a summary of the content. So the basic goal was to a spectral problem, right, to investigate the spectrum of this Fröhlich and other polaron models of this kind. In particular, the model at fixed zero total momentum, right, where you actually have a discrete spectrum, you have an eigenvalue, and then you have an essential spectrum. And the question was, are there any excited additional eigenvalues? And we show that at weak coupling for all these models, there are none, actually. I find as a spectral problem, this is really intriguing because it's one where you apply the usual tools. Say you apply the Schur complement formula, you apply the Biermann-Schwinger principle, and you're led with sort of a Biermann-Schwinger operator whose lowest eigenvalue is identically zero, irrespective of the coupling. So it's like I said before, it's like a system that's always critical, right? But just doesn't go beyond critical. So in some sense, the next eigenvalue is always at the threshold of being there, but never appears. Okay, so this I don't know if you've seen anything like this ever in another spectral problem. I haven't. There are some various open problems. Actually, one thing is a bit annoying. I fixed the total momentum to be zero, but actually it could be any other value, right? So the picture is what you really have is a family of operators that's indexed by some total momentum. Let's call it psi, right? And you would look at psi minus p squared plus phi plus n, right? So this would be the model where you fix the total momentum to be psi. In my case, psi was zero, but psi could be any other value. And in fact, if you plot the energy momentum spectrum as a function of psi, right, you expect something like this. There's a parabola that's sort of the mass shell. Sorry if it doesn't look quite like a parabola. That's the mass shell. Here is the one. And here is sort of the essential spectrum. So you would have here essential spectrum here, but you have the isolated mass shell out here, right? So we only looked here at psi equals zero, but at any other value psi, if psi is not too big, you will also have this isolated eigenvalue. And of course, the fact that there are no additional eigenvalues here means there shouldn't be anything either at non-zero momentum. But the proof actually does not work, since the proof is sort of by explicitly computing something that I cannot compute for non-zero momentum. I cannot actually prove that there is nothing at non-zero momentum, but it's certainly not expected. So this is an open problem. Now, I think from a physics perspective, it would also be interesting to know quantitatively how big can the coupling be, or how big does the coupling have to be until first eigenvalues appear, right? I mentioned at the beginning that for the Fröhlich model at least, but I'm sure the analysis applies more generally, we can prove that there are lots of eigenvalues if you make the coupling big. Interestingly, they have not been predicted and also not seen anywhere in the physics literature as far as I know. But then if you look, and people have done quite some heavy and sophisticated numerics on the Fröhlich polaron model, but it's always restricted to relatively small coupling. So usually one works in terms of g squared, that's the natural parameter that's called alpha usually for the Fröhlich model. So the numerical simulations I've seen, they all stopped roughly at alpha equals 10, and they have not seen any excited eigenvalues. So I would actually like to know how big does the coupling have to be before they appear. I know they appear eventually, but apparently that may be beyond the numerical capabilities. So I think that makes the problem maybe even more interesting, but there's certainly lots of open questions. So I'll stop here.